interesting that one of the largest representation present are from Argentina with Felix Mirabel and others. But especially the example given by Dili, which arrived from Beijing directly to the airport in Pescara in time. And this was an example for everybody to follow. But his presence is much more significant than just his organization of the trip. He is now an adjunct professor of ICRANET, is a representative of a tradition of collaboration between ICRANET and China, and we have been all happy to see the return in which of Professor Dili to Tsinghua University, where not only him, but also his family, his father, represented an extremely important link for the relation with ICRANET and ICRA. It's a great, great joy to see him. And it's a very, very special moment because changes are happening every moment. Every moment the world is having difficulties, larger and larger. But we are relieved that at the same time, in our field, every moment there are new scientific results. And I will try to make an effort to explain to Felix one of the key new ideas that we are following. Is still in the beginning phase, but it looks promising. And it was inspired to me by your talk. It's a simple idea, but therefore I don't exclude that between the people present here and the people online, we will have a great meeting. We have a great pleasure to have here with us, of course, the new president, not new, but since a few. 2023. Yes, therefore now from 2 years active and making a great change. Wang Yu as director of ICRA, with the other organization organized with ICRANET, and the mayor and the Pescara University UDA, hoping that Piero will join us shortly.
I think for my first contact with this meeting, it was like my interview. It was 2011. Professor Rufinho was holding this meeting in Beijing in the National Observatory of China. Then I was invited to give a talk there. Then during the talk, you recognized me and accepted me as a PhD student working in Sapienza. So already 14 years passed. Now I'm happy I can I partially chair this meeting. And these days, we are working a lot on the AI. We have students and professors applying AI. So some specific neural networks also including the large language model on gamma ray bursts, on supermassive black hole, on fast radio burst, on the James Webb data, a lot of things. Then we decided this year, I think we finally registered a company, not company, institution in the United States last month. So now we have another new institution called the ICRANET AI. And we welcome everyone to join and work on it. Thank you.
And let's see if Professor Di Carlo is there. Yes? Piero, puoi dirci qualche parola?
Hello.
A very important contribution of the University of D'Annunzio has been to give, in a very difficult moment, two students for 3 years on a PhD program which started in collaboration with the USTC in Beijing and the University of Ferrara, and of course ICRA and ICRANET as founding member of the JIRA PhD. We have to shortly to go and check what is the situation, because now the great contribution, believe me, in this condition, to have two fellowship of 3 years to two students to start to go on the JIRA PhD and propagate becomes very important. And especially now that Professor Dili is here, I would like him to visit the campus of UDA, meet the rector, because more than ever, we need to make real this PhD program with the University D'Annunzio. It could be initially an electronic PhD, and we have even a name for this PhD, Alessandro Valignani PhD program, to open the participation of China, and similar to what Alessandro Valignani, who was born near the University D'Annunzio, few kilometers away from the campus of the University D'Annunzio. Of course, this was in the 16th century, but still is significant. And this man started from here, went to Portugal, from there to Goa, I found a university, and from Goa I went to Macau, I found a university, and from Macau went to Japan and found another university. We want to keep going with this tradition. Puoi dirci qualche cosa?
Yes, hello everyone.
Sì.
It's a pleasure for our university to collaborate with ICRANET, with Professor Ruffini. As he mentioned, we are supporting two PhD students, and I think that for our university is really important, this collaboration, because this is an excellent ICRANET that is pretty close to our campus, so it makes sense for our students, for our colleagues to have a joint activities with you, because together we can do as much as possible new research program, as mentioned, new activities. So I think that this is just the first step, but we hope that in the future we can make more and more collaboration with you at ICRANET, but also with all the partners that used to collaborate with ICRANET. So unfortunately today the rector is busy, so I'll give you greetings from him, from all the academic people of our university, and I hope that you can work together. I'm pretty sure that you will have a nice meeting as a tradition of this meeting that obviously is a long time ago that Remo Ruffini started this meeting. So I'm sure that you will enjoy working together in the meeting, and you will also enjoy our city, and hopefully we can meet here in our campus. So thanks for the invitation, and I hope that you will have a great week of meeting in Pescara.
Thank you. I think you keep in mind that Dili will be here for all the week, and we would like to visit both the campus in Pescara and in Chieti, and then we will visit from there the birthplace of Alessandro Valignani, a few kilometers away from your campus. I pass now the microphone to Professor Dili.
Well, thank you, Remo. Can I, since this is the environment I like, it's quite relaxed. Can I sit down? It's a little bit relaxed. Try to make back some time. So here is this is not a very coherent talk. It's some update about the projects going on with the FAST telescope and some of my recent thinking on detection, particularly in the radio band. So here is the man that requires no introduction here. Galileo's usage of telescope initiate modern astronomy, and he's also the man that initiate modern physics by thinking about basically the relativity of motion and force, and the combination of new information about the celestial bodies and the underlying principles leading to the sort of heliocentric cosmic perspective today. So continue on the sort of modern physics and astronomy tradition, Newton at the time, and also practically most of the physicists at the time is thinking about two things. One is navigation, the other is war, so how to shoot a cannon. So one of the representative questions is that you give it a larger and larger explosion, the cannonball will travel further and further away, and Newton realized that essentially you are changing the curvature. So what happens when you have the curvature equal to the curvature of the Earth, right? And that's leading to the theory of the classical theory of gravity. In doing all this, as well as inventing the whole mathematical infrastructure, there's one unsolved classical question that Newton raised, which is the bucket problem. So if you rotate the bucket with the water, and eventually the water will have a curvature. Now the question is that if you see the curvature, then in what reference frame the water is rotating about? Because it started, the bucket is rotating, the water is not. Then eventually the bucket and the water is co-rotating together. But if you imagine, if you take away the bucket, then in some reference frame is may still have this curvature, and this actually has been looked upon repeatedly. And the Ernest Mach, being both a physicist and a philosopher, actually gave this quite brilliant answer. He says, well, it depends on the size of the water. So he's thinking about, if you look at the ocean, can you see the curvature? And if you push that thinking to the extreme, he says, well, if you have to insist on the surface of the water of some arbitrary size, that it has to know it's in some rotating motion, then it can reference that motion to the stars. So that getting into the regime of cosmology, but the core difficulty here is that whether there exists on some scale a absolute reference frame. Is it the vacuum? Is it the ether? So by the end of 19th century, Lord Kelvin had that famous speech, and I actually found out online it was also published based on his words, an article. The title is "Two Clouds over Physics," and one is the whether there's any detectable relative motion of microscopic objects, such as a planet relative to ether, since the light has to travel in some medium. The other is the black body problem. So in respective to whether you have this absolute reference frame, in conjuncture with this question, there is also the difficulty of gravity, which has been well recognized by Ernest Mach, in that the gravity itself, by being only has attractive force, making it impossible to construct a stable system in the limited frame, because everything will go. If it's in a system dominated only by gravity, then 2-point mass or any point mass will eventually come together, and when they touch each other, the space disappear. If the space disappear, then so does the time, and the whole space-time construct. And I think this is the difficulty that since Albert Einstein is very familiar with Ernest Mach. He reads and taking notes of Ernest Mach since his teenage years. I think Einstein's construct is that if you equal the gravitational force to the geometrical property of the space-time, then when the 2-point mass getting closer and closer, then you get greater and greater curvature. So that way, it's kind of circumvent this sort of immediate collapse of the whole space-time. You just go to larger and larger and curvature. But that leading to, I think, the still outstanding problem of the singularity within the black hole, since there should not be any infinity in the philosophically in the current observable universe. So almost immediately after the speech by Lord Kelvin, Max Planck sort of solved the black body problem. So at the beginning of 20th century, Planck has two articles, Planck 1900A and Planck 1900B. His starting point is try to fit the black body, measured black body energy spectrum. So at the time, there are two types that readily available. One is that if you're working in the iron industry, you can hit the material to thousands of kelvins in modern units, and you can measure its heat output. But the better data come from astronomy, which is the stars, particularly the sun, and there's the so-called ultraviolet catastrophe. And Planck, being a theoretical physicist, says, well, let me try to construct a black body based on what theorists know full well, which is springs, or harmonic oscillator. So he just put a bunch of harmonic oscillator in the closed system and let them exchange energy fully. And what he realized, historically, it's not very clear whether he had this realization first or he actually have to guess the functional form first. My guess, he guessed the functional form first, but he realized that it can be readily explained if you just bring in a prior, which is that there is a frequency-dependent minimum unit of energy. So instead of a continuous energy, now you have a discrete system. And any discrete system is equivalent to a wave system. So you basically bring in the phase. And so that's and with the data available at the time, he was able to actually fit this so-called Planck constant. So by the very early stages of 20th century, now we have relativity, and we also have quantum. So that brings us into the sort of modern physics, as well as astronomy. So by 1930s, the modern astronomy initiated by Galileo now come into the modern epoch, meaning that we are now doing real optical surveys. We are looking at the sky, not object by object, but with the first the film, and then sensors doing that modern survey. So this is an article written by Freeman Dyson in memory of Fritz Zwicky, who lead this effort in 1930s. So the first sentence of that short article titled "The Dynamic Universe" reads, "The first person to carry out a modern survey of the night sky, Fritz Zwicky's astronomical observations led to a new picture of a turbulent universe that is punctuated by violent event." Which means when you have a larger field of view and has a persistent surveying of the sky, you can start to realize that a lot of objects on the sky or phenomena are changing. So it used to be if you just take a film and look at one area of the sky, you may not get back to the same area, except maybe a planet. You try to follow a planet or comet, maybe next year or even say next decade. Now, if you look at the sky, say same area of sky every day, the majority of the object in that little square actually changes every day at some level. So we are living in a so-called, Freeman Dyson's dynamic universe. It's basically a changing universe, and the scale of changing exactly depends on the cadence of our sampling and the accuracy of our measurement. So getting into the 20th century, particularly in 2007, radio astronomers, represented by Matthew Bills on the left, Mauro McLaughlin in the middle, and Duncan Lorimer, detected the first fast radio burst. And this is my personal count. So since year 2000, there have been 19 Nobel Physics laureates was awarded the prize for 10 separate achievements in 7 years. And Shore Prize only started in 2004, but it has a separate prize for astronomy. This is let's see whether it can get the. Unfortunately, it's lost some of the names, but for basically the accelerating expansion of the universe, gravitational wave detection, and Peoples for cosmology, and Mayer for exoplanet, and the galactic center supermassive compact object. The Shore Prize Committee, which was organized by the Shore Foundation in Hong Kong, so it's independent from the Sweden Academy, were able to give the Shore Prize in advance of the Nobel Prize, which to me is quite fascinating, because there's two committees and they have different priority and focus. It's kind of reflect two things. One is the sort of the classical or the fundamental physics that we know full well in 20th century, kind of getting slow, like discovery of new particles, unification of the sort of grand theory development. In a way, after the BCS, the superconducting theory, I think we're not seeing such sort of pure theoretical work. It's not pure theoretical. It's major theoretical advancements in fundamental physics yet. But in astronomy, it's actually there's an accelerating pace of generating impactful discoveries. So this is the first fast radio burst. Let's see whether I can have the sound. No. Is it possible to have sound? Let's see. Sorry. No matter. That's okay. So this is the sweep in the so-called dynamic spectra. So the x-axis is the time, and the vertical axis is the frequency. And this particular radio explosion, we think it's a delta function in time when it's first appeared. But when it travels through intergalactic space, it got dispersed by the plasma. It's mainly the warm or lukewarm electrons at the temperature millions of Kelvin. And in such propagation process, the higher frequency part of the wave has faster speed of light, so it's arrived or detected by the instrument earlier. So you can see this, hear this tune. And the main challenge of this team at the time is that they only have this one signal with a the dispersion measure much larger than any of the pulsar previously seen. So if you project that to a distance. This burst has to happen outside of the Milky Way, and the intrinsic brightness or intrinsic energy is about 20 orders of magnitude of an average pulse from a pulsar. So it's really unbelievable, and so they go back to their survey to try to find other similar signals, and it's not there. And within the same year, their colleagues at the same Australian observatory, the Parkes Observatory, also detected similar sweep from microwave. So when you open or close the door in the coil, there's a sweeping movement of the electron that also produce extremely strong sweeps. But there's other characteristics that you can help to distinguish this, which makes their results even more doubtful. But they managed to get it published, and at the last sentence of the opening paragraph, this authors made the claim that not only this is real, but also hundreds of similar events could occur every day. This is not too surprising to me as an experimentalist. So, but it shows the confidence of this bunch of people in how they calibrate their data, how they draw up their design, right? It's a survey, so you have a sky coverage within a certain number of time, and you have to assume some average event rate. So their discovery managed to bring this field from 0 to 1, and they are now projecting 1 to 100, which both are giant leaps of faith. But fortunately for them, it was like 7 years later, there are 4 other discoveries from an independent survey. That's only make this field sort of somewhat believable. So the real landmark discovery is in 2017. Before this, before 2017, the status of the field is that someone see like one giant pulse, and it has some special trait because every measurement is new. So now someone start to measure polarization. Oh, you see, it has a flat within that narrow band. It seems to have a flat energy spectrum, so on and so forth. So basically, it's a discovery science. So someone see 1 or 2 and publish a Nature Science paper. But in 2016, the Arecibo telescope, still the largest telescope at the time, discovered the first known repeater. So that completely changed the status of the field, because now you have a fixed target, and you train every kind of telescope or instrument you can get your hands on and try to look at the source, and also coordinate with the radio guys to see whether in the same epoch there's radio explosions. And that result in the first localization by a very large array in United States, and also the detection of the optical galaxy and redshift, and also there's a radio source, the first known persistent radio source, which means even when the fast radio burst is off, since it's for each individual burst, it lasts somewhere between like 1 millisecond to 100 milliseconds. It's quite short, but even when it's off, there is some faint glow that is always there. So it's really changed the field. Now with optical redshift of the host galaxy, you can now estimate its intrinsic energy, and it turns out the first estimate is right in the ballpark park. So I like to use the solar radiation, the full 4 pi solar radiation as an energy unit. So a common fast radio burst in a few milliseconds can contain a full year's worth of solar radiation, and it is it's about 10 to 20 orders of magnitude brighter than a normal pulsar. So the fast radio burst, the first repeating fast radio burst was the last great discovery from the Arecibo telescope. It was first established in 1963 and lasts until the end of 2020. And in 1973, Arecibo discovered the first double neutron star binary, and in the subsequent 2 decades of follow-up timing, it shows the periastron precessing, and it's basically a direct evidence of gravitational wave radiation that won the Nobel Prize in 1993. So if you look at it's very rare in modern times for a scientific experiment or instrument to lead the world for like half a century in a field that is growing and quite active. So the great Arecibo telescope was a direct result of the Cold War, particularly spurred by the Sputnik, the successful launch of the first man-made object to go around the Earth, the Sputnik satellite. United States established 2 agencies: one NASA to man to operate the space program. Another one is called Advanced Research Project Agency, or ARPA. And ARPA was later transferred to the Defense Department, so it's DARPA, and it still exists today. But the first major project of any kind was the investment into this giant antenna that we radio astronomers all benefit from and really have no complaint. So healthy competition is good for fundamental research. Otherwise, it's hard to imagine that for any national government to invest in something that is practically crazy, right? It's unproven. It's 10 times larger than anything exists at the time. You really have to have some strong motivation for doing such exploratory experiment. So the Chinese effort in this area, and practically in all astronomy, was started in the middle of 1990s. That was first proposed as a candidate concept for the square kilometer array. So the square kilometer array referred to its collecting area. It doesn't necessarily have to be like 1,000 small antennas, right? It could also be like 10 giant antennas. In fact, the founder of the whole project, Dr. Ren Dongnan, was dreaming about 20 such Arecibo-like antennas. Depends on the size of the depression, and then you can add up to the SK collecting area. But that's what one of the 20 survived, and that's what we have built today. So it has a diameter of 500 meters. If you have Statue of Liberty lying down, you can 5 consecutively. It's a it's part of it's not a half shell even, it's a part of a spherical cap of a sphere that with a 300-meter radii. So we're slightly less than half of that shell. So that's the night view. And you can see that spiral of light is a truck that is in this time delay photo, that the truck was driving on the road in this spiral. And so the whole connecting area was filled by holes about half a centimeter in diameter. So more than 50% of the collecting area were actually empty. So that saved the weight and metal and money. The operating wavelength is around the hydrogen band. So that's 21 centimeters. So half a centimeter is less than 20th of the wavelength. So it's still a proper reflective surface. And that's the engineering concept. Since it's too big to move as a whole, we break the whole surface area into 4,500 small, well, it's decent triangles. So each triangle is about 11 meters on one edge. And by changing the position of those elements, you can change 300 meter of the larger 500 meter spherical cap into a parabola. And the parabola and the sphere of the same curvature radii of 300 meters. So that minimizes the absolute distance you have to move each panel. So each panel move within about one meter range. If you stand beside our telescope, it's imperceptible since it is a 500 meters, so it's move slowly. But that realize you're moving this 300 meter parabola shape in this big walk of 500 meters, so that realize tracking and changing of sources. And this whole thing cost about $180 million, and the construction lasts only 5.5 years, and it's really an engineering wonder to behold. We started operation in early 2020. So now it's currently running about 400 projects with scientists from 30 countries. It's roughly generate 100 papers on academic journals every year, and 2 to 3 Nature or Science papers every year. So its success has far exceed my own sort of personal estimate, and I believe most of the people that are involved with the project. So in late 1990s, I was a graduate student in Cornell University in U.S., which proposed and have been managing the Arecibo telescope for most of its lifetime. So at the beginning of 2000, along with the observatory director at the time, Paul Goldsmith, we published this little work on the self-absorption of the hydrogen line. So it turns out that once you increase your spectral resolution, there are very common narrow H1 self-absorption lines, and we call it a self-absorption because it's spectral absorption of the spectral photon, but it's not mixed gas. It is foreground cold hydrogen absorb the photon from the general galactic H1 background. So the cold neutral medium that is permeated throughout the Milky Way with a thicker disk, much thicker disk than the stellar disk, usually is at 100 Kelvin. But for the star forming regions, there are molecules, and molecules are much more efficient coolant. So the molecular hydrogen can collide with the residual atomic hydrogen, cool it down to about 10-20 Kelvin. So a 10-20 Kelvin gas projected against 100 Kelvin background is very clear. Once you have the resolution, it becomes very clear. So ever since then, my colleagues and myself have been trying to use this so-called H1 narrow self-absorption, that's a name I invented, Hinze, to measure its Zeeman effect and to measure the magnetic field, but it's unsuccessful for about 20 years. And in between, I go back to China, work on the FAST telescope, and Dr. Ren Dongnan is on the upper right. And we also get a great guidance and collaboration from a bunch of international experts, in particular Carl Hayles from Berkeley, who is one of the pioneers of trying to measuring interstellar magnetic field. So we managed finally to get the Hinze-Zeeman, first Hinze-Zeeman measurement and measure a rather weak interstellar magnetic field in molecular cloud at about 4 microgauss. So this was published at the beginning issue of Nature in 2022. And last year, Chinese government actually endowed upon Professor Hayles this friendship medal, and since he's retired, I don't think that caused much political trouble for him. Just show our gratitude, and this is just show that we have our great example of Arecibo telescope, and FAST is 2 to 3 times more sensitive with modern electronics. But while we are doing this more quote-unquote traditional science area of H1 and pulsars, there's this great new field of fast radio bursts that is transient, that you don't know where it's appear. So there is this urgent need of try to do simultaneous survey. So while we're carrying out the designed purposes, we should also be able to record and try to search for fast radio bursts. So by the time of 2018, we designed and realized the so-called CRAFTS survey mode. It's a shorthand for Commensal Radio Astronomy Fast Survey. It's the first such survey of its kind, because in the history of radio astronomy, before FAST, that including Arecibo, GBT, Parkes, and so on and so forth, there have never been a survey that will observe the same area of the sky just once, but can produce data stream for hydrogen pulsars and transient together. And this is based on this novel calibration technique, is so-called high cadence Kell injection, which I won't bore you with. There's some. It's the concept is actually quite simple. It's just that the modern computing and electronics were properly used. So I usually like to show this video, but it's not necessary just to show the concept of how this mode function. So in about 5 years now, This drift scan survey is a blind survey. We just reform the dish and 300 meters of it to a parabola antenna and point it at some declination and just let the Earth rotate. And we have, so each beam is about 3 arc-minute across, but we have 19 receivers. So it lay out this pattern, and this pattern cover about 20 arc-minute in deck. We have covered about 5,000 square degrees now with more than 220 confirmed new pulsar discoveries, including more than 60 millisecond pulsars and 3 double neutron stars. And there's a systematic effort to try to do follow-up timing, but it take a lot of time. And all the confirmed discoveries with its necessary information and published data set are all available online. So this is the H1 data cube. So each slice is about 1 frequency or 1 velocity. So you can see in this about 300 square degree toward the Orion star forming region. There's many filaments and bubbles, and they are being blown out by the massive young star clusters. And this particular little heart-shaped bubble is quite famous. It can be seen in optical infrared and ionized gas, and now we also start to see it clearly in the hydrogen gas. Back to the fast radio burst. So while we are drifting past through the sky, we have quite a low detection rate, because even for this 20 arc-minute field of view, it's not enough. It's sort of going off in random directions. And on this graph, the x-axis is the redshift estimate based on the dispersion measure. So we go from the big band to the current redshift, and the vertical axis is the measured flux times the distance squared in the unit of solar radiation. You can see the different symbol represent discoveries from different telescope, and it's dominated by little white dots. That's from this one very successful experiment from Canada. It's called CHIME, because it's a simple array. It's designed for H1 intensity mapping, but it's known for transient. And I'll try to go quicker. So it has a modern beamforming array. It's basically computers, the digital beamforming of so provide a 200 square degree field of view. So that's explain its success. So our survey only has about 10 new discoveries. So it's really a small number, but we are a relatively unbiased blind survey. So from craft survey alone, we can derive a empirical all-sky fast radio burst rate at more than 120,000 every day. So which basically means it go along this roughly flux to the -2 power law luminosity function. At the fast sensitivity threshold, we see no sign of it turning off, so it still keep exploding. We also have this so-called first persistent repeating fast radio burst discovery in 2019, so-called 190520. So the only about 5% fast radio bursts were known to repeat. And within this 5%, only about 10 that are very active. But except for this 190520, all other sources are known to turn off. So even though it may be very active, like 121102, produce hundreds of bursts every hour, but then it's just gone for months. And this source, ever since its discovery in 2019, just keep producing bursts. It's minimum like 1 in 20 minutes when we look at it. It also has the second known persistent radio source counterpart. So when the burst is off, it also has this very supernova remnant-like radio flux. So in many ways, 121102, the first known repeater, and 190520 looks very similar. So they are also well localized to the peripheral of a metal-poor dwarf galaxy. So the dwarf galaxy roughly has a size about 5 to 10 kiloparsec, and the metallicity is only about 1/3 of the galactic value. And they are also very active, and they have similar absolute brightness of the persistent radio source counterpart. And they also have excess DM that is outside of the cosmic variance of the so-called McCord relation, which has been used to probe based on the dispersion measure of the fast radio bursts of the baryonic content of the universe. But it's but this only happens in very active repeaters, so I think it's still a robust conclusion that roughly 50% of the baryon exists in intergalactic electrons. This is also an opportunity if we can somehow associate the localized dispersion measure to the property of the fast radio burst. It can help us refine FRB as a cosmological probe. This is a very active area. So we also regularly monitor this known very active repeaters, particularly 121102. We managed to catch an extremely active episode also in 2019, but it's published in 2021. So you can see this river-like burst. This represents real bursts from 121102. And based on this 1600 burst, we can, for the first time, construct a burst rate and energy spectra. So we can get the characteristic peak energy, which means that below this energy, the burst rate starts to drop significantly. So it has a characteristic energy of about 5 times 10 to the 37 erg. When you go to the higher part, it now mimics the commonly assumed power law shape, and this goes beyond 10 to the 41 erg. And so I use a log normal to fit the low energy part, which tend to represent some stochastic processes. And the higher energy part, I use a Lorentz-Cauchy function, which commonly used by atomic physicists. It can be chance association between two random events. So it's this so-called Lorentz-Cauchy. Just you have some, it starts out flat, and then you go to higher and higher energy, the probability density function goes asymptotically approaching some power law. In the classical case, it's approaching -2. So in the -2 case, it can be reconstructed by just take the ratio between two random Gaussians. So it's a rather nicely functioned form. And now we have a collection of active repeaters that bring us rich information. So this is the x-axis is the bursts that were observed in different bands in terms of gigahertz, and different colors represent different sources, and different symbols represent different instruments. So it's a little bit messy. And the vertical axis is the degree of linear parameterization. And one thing we realized a few years ago that it has this unifying trait, which is if you go to higher frequency for the same source, it tends to go to higher degree of linear parameterization. And this is exactly prediction out of plasma physics. So if you have a single vector, which is 100% linear polarization, once it goes through a plasma, it has Faraday rotation, so the vector will rotate. But if it goes through a complex plasma, a different chunk of the same phase of the wave may rotate slightly differently. And then when you collect them at the telescope, it will be smeared. It will have this depolarization effect. This is so-called multipath scattering. It has been well known ever since the 1960s. And it has this steep dependence of lambda to the fourth power in the exponential. So that's why when you hit a characteristic frequency, just drop like a stone. And its function together multiplied by the so-called sigma Rm to the square. So sigma Rm represents the local standard deviation of the rotation measure, which is integral product of the magnetic field and the electron density. So that just reflects the degree of variation or degree of complexity of the plasma along the line of sight. So we further hypothesize that the more complex the environment surrounding the fast radio burst, it means that it's younger. So this has not reached a consensus yet, but the sigma Rm, I think, is one of the more robust and useful tool that coming out of the observation of fast radio bursts. So this my like $5 animation of how the FRB was made, but it's not too scientific yet. So I will just for the sake of time, let me go directly to the conclusion part. So, where can I? Okay, oh, here. So there's so the whole field is still in the early phase. There's new phenomenon to be discovered, and there's well, there are two parts of the sort of the theoretical aspect. The first part is counterparts. It's astronomical origin, and that part I think is quickly converge onto some sort of compact object, and with the magnetar being the leading candidate. That's because to produce strong coherent emission, you want some persistent strong magnetic field, and the compact objects are the best class of known celestial bodies that have that trait. And the second part is kind of hopeless, is how to produce this coherent emission. I have estimated that in the fast radio burst, well, say in the pulsars, normal pulse, it can contain like 10 to the 24 photons. That's because the radio photon, the individual photon the energy is very small. So even for a pulsar that give you, say, 100 pulses every second, each pulse has 10 to the 24 photons. And the current day physics just has no way to concentrate that much photons in that short period of time and let them still in coherence. So when they come out and travel whatever short distance in the magnetosphere of the pulsar, you just cannot keep holding this large quantity of photons together. That's so-called coherent lens problem. So if we don't make progress in the emission physics, sort of the fundamental aspect, it's very hard to come up with some coherent solution to now like 20 orders of magnitude more, now 10 to the 44 photons. But that shouldn't stop us to solve the origin problem first. So I roughly summarize all this information about fast radio bursts into three categories. So one is robustly known or measured, and one is educated guess, and the third one is hypothesis. And all three are sometimes oftenly mixed. So what robustly known is that it has to be some sort of coherent emission if we estimate the equivalent thermal temperature just by using the C times the T, which is the time that the burst lasts. That, because it's millisecond thing, so it's roughly the size of a neutron star, say 1 kilometer or 10 kilometer, and it gives such a giant energy. So if it's incoherent, it corresponds to like 10 to the 40 Kelvin, which is ridiculous. And another thing is has been proven to be extremely radio loud. So there is a galactic magnetar burst that has gamma ray burst, gamma ray flare, giant flare, has X-ray burst, and has measured radio flux. And that ratio of the X-ray energy to radio energy is about 100,000. And all the rest, because it's outside of the galaxy, so we can only see radio. Now we have a limit at about 10 to the 8th, and it's keep dropping. But regardless, it has to be radio loud, given its coherence. So these two come to that it probably some sort of compact object. And there's also that we know that fast radio bursts repeat, at least partially, because all the rest of the source, we don't know for sure they don't repeat. It's just that we don't quote them repeat yet. So there is a cumulative function of repeating fast radio bursts from chime, because chime keep going back to the same area of the sky. And so far that function is still slowly increasing. So we'll see whether it's plateau out at some point. So that means that the majority of the bursts probably come from some non-catastrophic event. That doesn't mean that you don't require a catastrophic event to produce that compact object. It's just that once you produce that object, it may last for a certain amount of time that can keep producing bursts. And for a number of sources, it clearly has some plasma shrouding it because we see the depolarization. We also see on short time scale that it has changing of the RM. So it may be a combination of the environment and its intrinsic, like near source property, like the magnetosphere. Sometimes it can be hard to distinguish. And we also, I skip a few slides. But every one of my colleagues and competitors are trying to search for short-term periodicity. But so far, out of 1,000 sources, there are only 2 robust periodicity, one at 17 days, the other at 160 days. So those doesn't look like the spin of a compact object, look more like orbital motion or some precessing modulation of the beam. For a compact object, it's probably should be like seconds or shorter. And we have done quite conclusive statistical work to show that we cannot completely rule out periodicity, but it certainly has a much higher degree of stochasticity. I think that still present a challenge to the compact object. So either it's very unstable because it's very young, or it is spinning, but the release of energy of the fast radio burst is not triggered by the spin. It's some internal, I don't know, the superconducting superfluid bubble that somehow just goes up and cause some quake of the crust. And there's different fancy stories that all sounds very interesting, but it's not well constrained. So in terms of the hypothesis, I think the magnetars, strongly magnetized neutron stars, are sort of leading candidate. But we sort of have to explain the repeating versus non-repeating, or like Wiki Caspi like to say that her view is that there may be a diverse origin or a diverse classes of object that can produce such bursts. So I have a counter offer. I mean, it's impossible to judge impartially its prospect, but I think it's philosophically more enticing in that I think most of the fast radio bursts come from one class of object, and its diversity in phenomenon come out of we are looking at the source at their different age, right? This is commonly done in astronomy. For example, stars, right? If you look at the stars, they are so diverse, but if you look large enough quantity, they actually follow some very particular track. So the origin event of the fast radio burst has to be some explosion, because we see the plasma that come out of this explosion, that so-called persistent radio source counterpart. And this explosion results in one or multiple compact object, and one or multiple of them start at some lifetime start to emit these very strong radio pulses. And at the early stages, at least, these radio pulses are very random. And you can see the pulses passing through this plasma and got depolarized. But the source will evolve. The surrounding supernova, quote-unquote supernova remnant, or the plasma bubble will diffuse. Now the source will become clean. But once the source becomes clean and polarization becomes stable, the activity level will also drop. So now you are primarily seeing, instead of a repeating burst, now non-repeating burst, once the burst rate drops to a empirically very low level. For example, if a source produces a burst every week, it's considered very active in the universe. But in current day modern surveys, it will be a single burst, because you don't know exactly which part of the 7-day, 24-hour, which second it have this burst. So even if you come back to the same sky every week, you may not be catching that phase, right? It may be the first burst come out on Monday of the first week and come out Tuesday of the second week. So you still don't see that burst repeating. This has the advantage, this evolutionary picture, is that potentially may explain the majority of the burst sources. So there are some immediate sort of expectations we can draw from this. One is that for the very early phases, when the ionized bubble exists, it lasts about 1/1000th of the total FRB epoch. So suppose a magnetar can emit giant pulses for 1,000,000 years, then this bubble lasts about 1,000 years. That are just some guess I made, but this ratio come out of the observables. It's a fraction of sources that has the persistent radio source counterpart. Right now, it's about 1 in 1,000. Two, if this early phase lasts short enough, we may be able to monitor a source and see a change. And this is very risky because if it lasts 1,000 years, you may not be able to see any significant change in 100 years, which is short in terms of cosmic time, but it's too long for any PhD. So right now, there are only one source that has monitoring data for like 10-year time scale. That's 121102, the first known repeater. So now we have a paper under review that we see its dispersion measure dropped by 10%. And that's at a 12 sigma significance level. So it mimics a expanding supernova bubble. My bet or my claim is that given long enough time and accurate enough measurement, all the active repeater, right now it's only about 10 of them, will start to show the decreasing of dispersion measure. It's not a variation, it's a persistent trend because the bubble keep expanding, and decreasing of magnetic field, which is the decrease of the rotation measure. So now we only have one. so just following Duncan Lorimer's lead. So now we're trying to claim from 1 to 10, and then we'll see. So this I'll skip the instrumentation part. Let me see whether. I have to things for this crowd. I have to quickly have something something crazy. So
Sorry.
Yeah.
I have a question before
Yeah.
you move to the
Yeah.
section.
Yeah.
So give me an idea, what's the time about? The time of the burst, radio burst duration about? How much time?
You mean how much
How
time?
much time burst duration?
The shortest duration now is microsecond, but most of them is a few milliseconds.
3 seconds?
Yeah.
Most.
Yeah.
And what's duration in time interval between the two bursts?
Right.
Most of them.
That's that vary wildly between source to source, right?
About 1 second, you say 1 second?
So the most active sources now we have in 1 hour we have 500 pulses, so that's a few seconds.
A few seconds,
Yeah.
review this.
Yeah, but for most of the sources, it can be days or even months. So yeah, one thing that
Here is 2 different dynamics.
I was thinking that it's
3 seconds.
yeah.
You're telling me this one interval between the two review this thing is more than second, even up to the days. So
Yeah, I was. My guess is that the younger the source is more active, so it has more sort of unstable energy holds there, so it can frequently release this energy. Then after a certain number of years, then it become fairly quiescent. So maybe a year, it has one.
after the seconds and even larger is sort of a hydrodynamic stuff. However, 10 minus 3 seconds, hydrodynamic scale.
Right. So it could also be one trigger, then there's some complexity in the magnetosphere. So there's one release of energy being separated into different burst event. That's the pulsar Fox picture. So that's the SAMB, but it's the SAMB already with dipole removed. And I was always puzzled by the existence of dipole, which give you a relatively clear, precise measurement of the velocity, the direction of the velocity and the magnitude of the velocity of the observer relative to the SAMB. So that's completely against the equivalence principle. So now you have a local measurement that can tell you this point A is different from any other point in the universe. So we tend to call the ingredient of the universe matter. They are interactions, forces of field. So there are 4 fundamental forces, and then for complex system like fluid, there are turbulence and other things. But all this for the observable universe happens in 13.7 billion years. That's a fairly short time. So my crazy thought is that the zero and infinity has to coexist, so they conjugate of each other. So if we accept that we live in a finite universe, that would mean that in our universe there's no absolute zero. So it has to be quantized. But the problem of the quantization is, one, there's no singularity. 2, it has also no absolute symmetry. If there's no absolute symmetry, there will be no absolute conservation or global conservation. In fact, the current observable universe doesn't conserve energy. So that's Aminath's theorem, right? If you want to have energy conservation, you have to have translational symmetry. But if it's a finite universe, you cannot just go infinitely forever on a certain direction, right? It's even more obvious if you have angular momentum conservation, then you have rotational symmetry. But if your axis has a point and somewhere, you cannot simply just rotate it. So which means the equivalence principle only work locally. So if you apply your equivalence principle on some finite space, which is much smaller than the 13.7 billion years, so we probably only have relativity. So all this thinking, what's the use of? So I recently started to borrow from the particle physicists. So they have this 2021 U.S. community report called Energy Frontier. So I think the experimental astronomy, the next frontier is so-called time frontier, because we cannot control the condition of the astrophysical quote-unquote experiment, but we can try to raise the cadence to sample the dynamic universe at quicker and quicker time. So the light or the electromagnetic wave is quantized. So that's E equals h nu, and it's quantized, so it can be described by a wave function. Once it's described by a wave function, then by the principle of the information theory, as long as we sample at twice the intrinsic frequency, we can get complete information. So, for example, for radio astronomy, the H1 lines at 1.4 gigahertz. Let's use 1 gigahertz for example. Then we only need to sample at a nanosecond, or 2 billion numbers every second. The information theory tells us that we get complete information of that field. You can sample 4 billion or 40 billion, but that doesn't bring you new information. Now, the question is that if at 1 gigahertz, we cannot sample much faster than 1 nanosecond, does it translate into that there's no phenomena in the universe that happen quicker than 1 nanosecond that produce 1 gigahertz signal? Right. So by the principle of information theory, if we observe 1 gigahertz electromagnetic wave, then the minimum unit of time we can obtain information is at 1 nanosecond. I sort of have a leap of faith. I say if we cannot obtain any information through the observation of EM waves, and EM wave is equivalent to the absolute vacuum. That would mean that in the universe, there's no physical phenomenon that produce quicker change than 1 nanosecond and also produce 1 gigahertz wave. 1 gigahertz. So you can still have, say, gamma ray burst that goes much quicker, but it doesn't have the EM signal at 1 gigahertz. Because if a wave cannot carry observable information, it basically means it doesn't exist at that cadence. And I have no proof of that. It's just a conjecture. All right, and to go even further, so when we look at this dynamic event, because of the quantized nature of the universe or the physics field, there is this conjugate quantity based on the uncertainty principle. So in Weil's original paper, the rigorous derivation is for delta x delta p larger or equal to h bar divided by 2. So that's the linear position and the momentum. And almost nearly rigorous is delta E delta T, which means you measure the duration of a certain event down to a precision, then times the measurement of the energy down to a certain precision, that should be bigger than h divided by 4 pi. Yeah, right. And
You are seeing that very, very small.
right.
But you cannot violate the H-bar.
Right. So we are still far from the H-bar level. But my thinking is that one of the primary goal is to design experiment or instrument to try to sample at different wavelengths, go to shorter and shorter cadence, and to try to get the maximum astrophysical energy or the brightest explosion. And the E, the absolute quantity of that energy, should be in the same order of magnitude of that delta E. The uncertainty you measure something should be in the same order of magnitude of that quantity itself. So I want to see in practice what the delta T, delta E product look like at different band. and so far there have been many orders of magnitude lower than the quantum principle. I mean, in the wildest dream, in the end, I'll see whether we can lead to some logic that we may be able to connect the age of the universe to the Planck constant. It may or may not exist, but philosophically speaking, it seems quite natural. If we have a finite time for the whole observable universe, then at the macroscopic level, this fundamental quantities should be related somehow. Right? This whole crazy guess. So, let me come to the end. So for the fast radio burst, it's relatively new field. We are still in the sort of cumulative phase, of trying to get more information. And the next generation of instrument, both from Canada, US, and China, I'm very optimistic that it will reveal the astrophysical origin in the next 10 years or so. And that the holy grail is to systematically find counterparts. So you have the radio explosion, you may have gamma ray or X-ray, but because it's extremely radio loud, it has to be really close. So you need large field of view monitor. But I think it will happen. So given the high event rate, so we keep building instrument, and someone will achieve this. And then the next phase, optimistically, maybe bring us some new fundamental insight. And personally, I'm more interested and optimistic on the real use of AI. For example, what Wang Yu is doing seems very promising, because for the past few years, every one of the papers in our group has some AI, but we are using it as labor, right? We used to have 2 graduate students look at 1,000 graphs every day. Now we have this program look at 1 million graphs. But it's not a sort of regime-changing thing. But I think we are now at the verge of really using the AI to do something that we cannot do just by simply scaling up labor. But it's still very early. Thank you. Sorry.
Question.
Yeah.
The decreasing dispersion of the signal is just in one source that has been observed.
Can you repeat?
The decreasing dispersion measure has been observed just in one source, and this is one question. And then the other question is it known what are the nature of the galaxy hosts? The general, the questions are related to the possibility of using fast radio bursts to do cosmology and go very, very far in redshift.
So far, we only have one source that show clear DM decreasing. My guess is that is a experimental bias, because this field is so new, right? The first localized repeater is 2017. So we only have this one source that has long enough time baseline. So my estimate is that given a few more years, we should be able to see in more sources. But that's still up to be tested. So in terms of the host galaxies, the very active repeaters tend to be in metal poor dwarf. Right? The metal poor dwarf galaxy. That's for active sources. But there's a recent paper come from the Caltech group. So they, in one paper, they localize 30 sources. They are all single bursts, and they come from all sort of galaxies. So I think it's maybe a probability thing. Maybe in metal poor dwarf galaxy, it has a higher probability of producing this weird compact object, and so you only catch them at the early phase, and it lasts a short period of time. But now, if you get enough stellar mass, there's always some chance you produce one burst.
I asked this question because I remember I worked on
Puoi essere così gentile di portare un altro microfono? Grazie. Regolarmente, non oggi.
Remember, in our galaxy, soft gamma ray repeaters used to be close to star formation regions, and then there was the famous soft gamma ray repeater in the Magellanic Clouds, where the metallicity are very low. So you think that might help to the studies in our galaxy of soft gamma ray repeaters to infer the potential of fast gamma ray bursts to do actual cosmology.
Vorrei essere certo che lei sta registrando tutto. Excuse me.
So if you look on the luminosity function, there's that transient graph, right? It's the x-axis is the duration times the bandwidth. So give you this the dimension is number. So there's this blob is the pulsar, and you go vertical, and this axis is energy. You go vertical up, this another blob is the fast radio burst, and the gravitational event is somewhere here. So you can differentiate coherent and incoherent. So there's this seemingly relatively empty space between pulsar and FRB, but we are now seeing that it's gradually being filled up. So at some point, if you look at the nearby sources, we may be seeing a continuous trend that connecting pulsars all the way to FRBs. So then it depends at what energy level you may be seeing, say soft gamma ray repeater related radio burst. You may not call it a fast radio burst, but it's only say 1,000 times weaker, but it's has radio, has gamma ray. Then you go up in this ladder. So it looked like this radio burst thing may be a continuous phenomenon. So it can happen at every orders of magnitudes of energy. It's just that happen to be our Milky Way has a lot of neutron stars, and they produce bursts in this energy range. Once you go outside of the Milky Way, you require extremely bright things. That was discovered first. Now, in the next 10 years or so, we maybe gradually fill up this phase space.
Può portare il microfono?
Yes.
Background noise doesn't help to hear well.
I always have this feeling that the ratio of repeating over non-repeating sources has been somehow underestimated. This is, I think, your point. Because of the rate, right, that this seems to be pretty high relative to the sources that, for example, we know could lead to magnetars. I like very much the idea that, for example, binary white-dwarf mergers could lead to magnetized objects and this thing, but even in that case, because these are pretty numerous sources that could explain the ratio, the rate of fast radio bars. But they are more or less at the limit of the relative to the rate of fast radio bars. So my question is, how much you think this fraction of repeating over non-repeating is being underestimated? And the second question is related to the in these new observations of graph of the pulsars, of the binary pulsars. So so you are going to, from the point of view of timing, so to look into p dot over p very low, very small. How small it will be? Like 10 to minus 18, 10 to minus 20, for example.
The second question first. So now our timing baseline is still short, like 1 year or two, and this pulsar timing business is you have to go like 10, 20 years. So now we are sort of just at the field average standard is 10 to the minus 15-ish. So it's still very relatively minor. The fraction of repeating bursts is a little bit complex because it also depends on the detection threshold. Because clearly, even for the same source, there are much more bursts at lower energy level. So to do this systematically, you more or less have to use one instrument. And currently, I think CHIME is the only survey that has that information. So we are all pay close attention to that cumulative fraction of repeating bursts. Because if it's keep going up, it means that there may be a lot more repeaters. But another possibility is at some point it starts to turn flat. That means you have in this cadence at that detection threshold. Now you start to complete cover the detection parameter space. Now then, at what percentage is turning flat actually tell you something more definitive. So far we haven't seen that chart. It's still it used to be less than 5%. I think now in the recent paper they say 7%. So it slowly goes up.
I have several questions. So first, I don't know if you have read a paper published last year or 2 years ago about they collected some magnet or pulsars emission and the spin period. Then they found that the observed emission period is always about 1,000 times of the spin period of the pulsar. Yeah. So which means we know from theory is a minimal spin period of a neutron star like 1 millisecond. Yeah. So you multiply 1,000 times will be 1 second. And also we have some older neutron stars spin hundreds of seconds or even hours. Then you will have days of the period. Yeah. This may be related to the.
Right. I don't know that word. Repeat again.
Repeat again is if you make a plot, the x-axis is the neutron star's self-spin period, and the y-axis is the signal's period. Signal, electromagnetic signal, radio signal. You can see the radio loud magnet or some transients. So you can collect signal. Then they follow a law, just a line. They follow a line. And this line, the slope is like 1,000 times. The y-axis is 1,000 times of the x-axis. Yeah.
I understand the question. So this is very relevant. I don't know this work very well. And so yes, so it's possible that the compact object of the FRB is stably spinning, but it only produces a burst very sparsely, so that smear out the potential detection. But there's another constraint, which is we basically do the waiting time, right? Just take the time that elapsed between each adjacent event. So even though you may have sparse signal and has a much quicker underlying periodicity, given enough substantial large number of signals, you will start to see regularity in the waiting time. So far, we haven't seen that. It's always looked like some sort of Poisson smooth distribution. But that doesn't completely rule out your picture, because we can still be undersampling if that's the case.
And you have one source that observes the thousands of the superbursts. Also, you have a collection of hundreds, thousands of bursts. But if you compare the statistics between one burst and so many bursts, what are the differences?
I think there have been a slew of such work, but we haven't done this on the fast data, because a lot of other people have done on chime data, because chime is more uniform survey. Because the single burst we see is through the drift scan, but the active burst is in a different mode, right? We stare at it. So it's hard to, statistically, it's hard to put them together. Generally speaking, the frequent repeat of a single source, I mean, one is tend to be much weaker, because that's how they are going to be seen. Two, it tend to be narrower, because the two is somewhat mixed. The fact it's narrower also means it has lower fluence. So we haven't done rigorous statistics to see whether we can separate the observational bias from the phenomenon.
Last one is about your last topic. Because in gamma ray burst, people think it's a tool to test the quantum gravity. Yeah, and quantum gravity. And normally we use the dispersion relation. On the left side, it's the time difference between two photons, and right side is the energy difference. And in gamma burst, we have the energy difference like spans 10 to 6 order of from MeV to GeV, so 10 to 6. But the time resolution is low. You have at most 10 to minus 3 milliseconds, usually in second. So I thought about this before, because in this radio astronomy, you have the time resolution spans 10 to 6 order of magnitude. And you have from megahertz to gigahertz, 10 to 3. So they are on the same level. They are on the same level.
Very interesting idea.
Yeah. So I think radio astronomy can do this testing as well. You are talking about to increase the accuracy. So it will be better than the GRBs. Yeah, for the accuracy.
Thanks. I'll have to leave.
Well, I
in this only persistent source that you said of 19 and so on, the dispersion measure seems to be outstandingly large, but the redshift is low. So I just want to understand, usually you infer from dispersion measure the distance roughly parallel to redshift measurements, of course. So what can this say about the baryonic contents of these galaxies? Namely, if there are, what I understood from this particular source is that dispersion measurement could be a local property of the source, not of the galaxy. This could be the reason, right?
Yeah. So that's also discussed in our polarization work, so-called sigma RM. So this source also has the largest known sigma RM. So that confirmed that it has a local environment that is with changing magnetic field and electron density, and it also has much excess of the electron density. So that density is concentrated around the source, not spread out through the whole galaxy. So we have a supporting evidence from the scintillation analysis. So those people who do so-called 2D dynamic spectra, which means you can do both frequency and time, the changing of light of that persistent radio source. Supposedly it should be relatively stable, but you see it's flickering. And from that analysis, you can derive a limit on the size of the region, because if the size is too large, then it's become very stable, right? Only when the size is small, you see that flickering. So we can say that the region that produce that persistent radio source counterpart is less than 100 parsec, and it's probably much smaller. It's that, but that's our measurement. So I think it's concentrated around the source. So I sort of also
This tells something about the origin of the source.
Yeah, exactly. So my hypothesis goes one step further, meaning that the more prominent the depolarization, sigma I, means is the PRS is smaller, means it's younger, and then this whole thing diffuse out. The measurement of the total baryon is probably still holds, because the majority of the measurement come from one burst, and that tend to be clean.
Thank you very much. We are facing a very important encounter. We are still on a very much calmer field, but I would like that our contribution will be interesting for you. And certainly your work is very interesting for us. Even we gave an award to this work, but it's becoming more and more impressive. What I would like to ask you is something peculiar. You have been writing a review, very extensive in science and so forth. I presume there are altogether at least 10. Can you give the secretary that we download all 10 of them and rush to read all the possible points as far as quickly as possible, to make sure to make this discussion more profitable? And from our point of view, the philosophy is different. We are just looking at at gamma ray burst and other related problem, and you will hear just next talk. And we are trying to understand better how the traditional physics, astrophysics, pulsar, neutron star, black hole, and so forth, participate in the GRB. And in particular, you will hear following the next talk, the possibility even that a concept like, but I would like to emphasize this point. We are understanding that our traditional supernova, neutron star, and pulsar, which we know, in the gamma ray burst acquire a different meaning. Because we see, for example, this morning, if we give still time, that there is an alternative to a supernova dictated by the gamma ray burst. And then we will hear things which have been out of the mainstream for gravitational wave, and looking at the electromagnetic information is more important in some cases than the gravitational wave. Of course, the gravitational wave, we are facing a problem, because there was one signal, then after 30 years there was another one, 7 years there are no, and we have doubts about. But this is another topic we will not treat here. Anyway, coming back, we are approaching to understand something important, that the presence of dark matter allowed to solve some problem which were not solved. For example, the one of the quasars. This will be an attempt done here, but we are classic, not trying. What my opinion is, where the thing could join, is that we are understanding that our field is much more complicated and much more rich. And I will not insist in trying to find the sequence. My opinion is that we are looking with your data to snapshot, very important. And even if out of this meeting, we will come to a new idea of, I hope we do, of having a new snapshot that you could try, this will be a great step. But the style is different.
Can I briefly respond? So I'm honored that you want to read my paper. My only response is there's no 10 paper worth reading, maybe 3, I think, because a lot of my work is experimental and it's later summarized, so it's maybe just 3 or 4. I think it's more than enough.
This is the best news you could give us, and I will ask the secretary to print immediately 10 copies of each, because everybody has to maximize the information. Okay, thanks. And now we can. Scusa. Sorry. Dove al coffee break? Sì. Quando devo parlare? No, parlo di meno. Va bene, 11:15? Cioè adesso? Ok, you go to the coffee break and I do something else which I'm supposed to do. If you like, you can hear. Something they ask me to give a contribution in a school. I don't attach any special meaning, but in a school in Russia, and I will have to speak there. I will say a few things, and then you will come back. Okay. I think we have to keep information going, no matter what.
Okay. Thank you. Are you hearing me? Okay. Thank you, Professor Ruffini, for the introduction. So, indeed, this is we are revisiting this. Actually, I put the GRB, but it's a short GRB, so a short duration gamma ray bars. So, for sure, you know, they are considered to be neutron star binary mergers in the literature, but it is not clear yet. Yes, there is probably the light from this window. I don't know. It's oh, it's blocked. I don't know if there is something. Is there? Okay, let's see if. Okay, better now. Thank you. So the processes at work in a short GRB, even if we consider that they are a neutron star binary merger, are not clear so far from the literature. And not all neutron stars binary mergers are going to lead to a black hole. That's why we added leading to a black hole. It's not that all of them should. I will get to that point, but it's important that we see this difference right away. So what is will be very important, as in any GRB analysis, as also as we were just discussing on the blackboard in the kitchen, is that the timeline of the object. So the timeline of the observations. So just to show you, just to recalling you the source, this is the light curve, specifically in the gamma rays from MEV energies to GeV energies. This is how this short GRB looks like. So you see this spike structure, but this spike structure is not all over. So you see one peak here. This is here. You will see here the main peak, what is called the prom emission of the GRB. There are following a spike structure of these three peaks we are going to speak about. And there is also this GeV emission represented by these green points. And there is also an X-ray afterglow emission from this source that we will speak about later. This is roughly the timeline. This is time. This is a rest frame time of the object. And here you see the luminosity in error per second. So this is what we call a precursor. So this is the first peak. Here is the main peak of the pron emission. That is a spike structure, GeV emission. And from here also there is contemporary to this GeV emission, there is also X-ray emission down here, some lower luminosity. And for longer time, this persists, this GeV emission persists for over 200 seconds, and the X-ray emission persists over 30,000 seconds. So this is the GRB we are going to speak about. As Professor Ruffini mentioned in a paper in 2016, we published an analysis of this source based on a neutron star binary merger leading to a black hole. So the same as here in general view, but the processes generating this structure were different. We consider a different interpretation. First of all, we didn't consider the explanation from the precursor, even if we advanced the hypothesis that it was related, being a precursor related to the approaching to the merger phase, or very close to merger phase of the two neutron stars, because of the presence of magnetic fields. While we consider here vacuum polarization process leading to this MEV emission of the main peak of the pron emission because of transparency of electron-positron pairs generated around a charged black hole formed in the merger. That was the interpretation. And that's one of the main points here. We are going to shift to change that view. But it's not because of we want to change that view because we want to change, because we are dynamic and we want to change. No, it's not because of that. But because it is not difficult to see that the conditions for pair creation are already met at the point of the merge, when it is at the merger. So even before black hole formation, and these are, I'm anticipating some of the points here, are already met before the black hole can be formed. And so that's why we are forced to revisit our interpretation. So we're going to the details of this. And so this is our timeline. And so first, of course, we have the in-spiral, mainly driven by gravitational waves when the stars are far apart. We know that from binary pulsars. But as in the approach to the merger, or near the merger and in the merger phase, this is one of the results of this work. The presence of high electromagnetic fields, very strong. In the case of magnetic fields, over 10 to the 14 Gauss for sure. And this could play a role in the dynamics of the merger. And so in the, we will get into that point, but this would be very relevant in the analysis of the dynamics of the binary in the latest stages, probably in the few milliseconds before merger. Then there is the merger phase, in which we have the precursor and the prom emission of the short GRB, and where we have an electromagnetic configuration, which we are going to model as a rotating magnetic dipole. Okay, so rotating magnetic dipole, but there is also an electric field which is induced as Faraday induction. It uses an electric field, and we'll have also surface charge on the object that we will infer from the conditions of equilibrium of the system. And from this structure, of course, we will derive from the data what would be the values of all this structure. Then you have the prom emission, ultra-relativistic prom emission, which will be related to the pair formation, to the pair expansion, to the pair plasma transparency. And so it's related to the physics of how do you form these pairs. Then, by the way, in this, I'm mentioning also these the numbers that you to give you already the feeling from this. The precursor is lasting roughly 0.1 second. That first peak there, emitting 2.3 10 to 51 erg in that peak there. While the main prom emission, so that's second part from 0.25 to 0.35 seconds. So again, our duration similar to the previous one, but emits 10 times larger energy, almost 4 times 10 to 52 erg. And one of the main points of our analysis will be this structure that you see here. This is the spectrum of this prom emission of the GRB, in which can be interpreted as a convolution of black bodies that we are going to relate to the transparencies of the plasma. Then there are these spikes, these 3 spikes structure. Over here, this spike structure, then from 0.3 to 0.4 seconds, emitting roughly 1.7 into almost 10 to the 51 erg, from which we are going to advance a hypothesis that they are related, probably related to quasi-periodic oscillations of the material around the merged object. And then we have the GV emission. At this point is where we think the black hole is formed, so not before. So this is a physics before this point, to this point of the timeline, was all physics of this merged object. So a massive neutron star, fast rotating core, approaching the critical mass for gravitational collapse, but not yet a black hole. And this would be related to the black hole, this GeV emission. These light green points over here, the green, the GeV emission, that will allow the analysis of this in this model. Allows us to determine not only the mass but also the spin of the black hole that is formed. And of course, this is related with energy angular momentum conservation is related also to the parameters of the merged object, and so related to the parameters of the pre-binary components. And then we have the X-ray afterglow. The X-ray afterglow emission that you see, this the darker green in that light curve, and from 50 seconds to 30,000 seconds of data tell us that these in X-ray are emitted like 8.2 times 10 to 50 R. And from this we will get some, from this we will assume that it's powered by accretion onto the newborn black hole, and from this we can get an estimate of the mass of this matter around the object, and this is related with the mass ratio of the emerging components, because the amount of mass that can circularize, at least spell and circularize around the new object, depends critically on the characteristic of this, how symmetric or asymmetric in mass is the binary that merged. So let's go into the details. So to start, not only for the precursor, but also for the prompt emission, so the ultrarelativistic prompt emission phase, we have to set the electromagnetic structure of around the merged object. And so here we take a model of rotating magnetic dipole and with a surface charge. So this is a general configuration. This is can you find in the Ruffini and Treves paper in 1973. So this is a generalization of the solution, a classic solution of the Deutsch in 1955. So this is generalized. So you can see from the structure of the magnetic field over there, you see that in fact, it looks exactly like a dipole, okay, exactly like a dipole at around outside the perfectly conducting object. You see, but it's a dipole. That dipole has an effective magnetic field, that it would be the bare magnetic field that we have without surface charge, plus you have some terms that depends on the charge times the rotation parameter. And the rotation parameter, this tilde omega here, is you can recognize in Newtonian star physics, pulsar physics, angular velocity times the radius of the object divided by c, tells you how fast is this object is in rotation. And we will see that even if the object is pretty fast, this fastness parameter, so to give it a name, is of the order of 0.1. So still expansion series in terms of this parameter is good enough to extract the main properties of this system. And in fact, this is a solution that is approximation as up to second order in this parameter. So this is the electric field inside and outside the object. And so you can see here very well there is a monopole contribution Q over R squared, and here there is the induced electric field from the rotating magnetic dipole. This is a known expression. The difference is that here you see again this effective magnetic field. So here is actually a nonlinear contribution of the rotating charge, of course. So this is the general structure of this electric field that we are going to constrain somehow. So this is the surface charge density over there. you see the surface charge density that comes from the discontinuity of the electric radial component of the electric field. So we derive the surface charge density, and it shows again, as in the electric field before, that they have a monopole contribution, and the second term you see is the contribution from the induced electric field by the rotating magnetic field. And that contribution you see is like it will see as we are speaking about surface charge density. It defines a sort of effective charge in the sense that is given by this term. So again, the rotation parameter sign the bare magnetic field times r squared. So this parameter so has the same order. We will see, sorry, we will see that this parasecond term has the same order of magnitude as the first in the system we are considering now. What about the energy? The energy stored in the electromagnetic field is we can easily get it. Is given by this. So of course, it have a contribution from the monopole, and then a contribution from the magnetic dipole, and contribution from the induced electric field given by these terms. Well, so how large would be this charge there? So far it's not a fixed, it's a free parameter in that solution. Here we follow Ruffini and Treves' position that was to find the charge that would minimize the electromagnetic field energy. So assuming that the electromagnetic field configuration is a minimum energy state, then the charge, you can minimize this energy, and then you will find this expression for the charge Q. This is exactly what I mentioned before. You see that this charge that minimizes the electromagnetic energy is again depends on the product of this rotation parameter, magnetic field, and r squared is actually the other one, and they are the same order, both of them. And you can express it in terms of the angular momentum instead of the rotation parameter. You just, of course, take into account that the angular momentum is the moment of inertia times omega. You can write this expression into this form if you wish, in this one. And it appears the product of the angular momentum times the magnetic field. But then it appears that you see here two parameters. One is the compactness of the object, and the other one is the form factor from the moment of inertia. I mean, as you write the moment of inertia as a parameter k times mr squared, this is this k, and this compactness is m over r. So you can even play with this and see, let's see what will be the limit if you assume a black hole, but then, and you can start play by, we will not do that, okay? We will compute these things for the merged object of the system. So we'll compute what is K, what is the compactness, and we will get the number. Number is here. If you compute that, you will get like 2.82 JB. Okay? Instead, maybe you are more familiar with the charge mass ratio. Charge mass ratio is of the order of 10 to minus 5. So it's a relatively small charge if you think about the maximum mass of a black hole, for example, of a charged black hole, that is Q over m equal to unity. So here we are speaking of 10 to minus 5 charge to mass ratio. But this is still conceptually relevant for this problem. So then, of course, this Q over m, 10 to minus 5, to compute that, we have to put a value to J or to omega, to the radius, this, and to the magnetic field. For the magnetic field, we use 2 times 10 to the 14 Gauss. Now it will be, in a moment, I will show you why. And the mass, 2.4 solar mass, a radius of 12 kilometers. And for all parameters, this is the order of magnitude. It will be clear in a while why are these numbers, the relevant ones. So, having said that, we can estimate what would be the effect of that charge in some quantities. So we start with the magnetic field, and we see already from the theory that the contribution, okay, replacing by the value of charge that we have now into the system, we see that the contribution, it comes to the second order in the rotation parameter. and the contribution to the magnetic field observable at infinity, the electromagnetic energy. So the contribution, it comes at second order, so it's relatively small. So to second order, we can consider the magnetic field to be the bare one, so without the effect of charge, for example, and the same for the electromagnetic energy that will reduce essentially to the one of a rotating magnetic dipole. And because the contribution will be of order 1%, of 1%. From this, it comes out now that if we assume that this energy powers the electromagnetic energy observed in the precursor, okay, we can attempt a constraint to the magnetic field. So the magnetic field, if we make that equality, assuming that there is some beaming angle, for example, here we can see that it will be of a few 10 to 15 to 10 to 16 Gauss for beaming angle between 10 and 30 degrees. This is an example of it. So already showing the presence of possibly the presence of very strong electromagnetic fields around this object. This is not, and these kind of fields are found in numerical relativity simulations of the in magnetized mergers of neutron stars. They have the field amplification even to this kind of fields. So it is in fact plausible to get that and explaining the precursor emission from processes regarding the release of magnetic energy of these fields. We can also look, for example, at the luminosity by computing just as the luminosity as the magnetic flux crossing the region of open magnetic field lines. And by doing that, we get this formula that is essentially, you can identify it as the formula of the spin down of a pulsar if you do this calculation. With the difference that you will have this luminosity even if it is not inclination angle. Then at merger, this formula, it is nice that the merger point, it reaches a value which is radius independent. It depends only on the magnetic field and mass. And if we normalize to the previous values that we were using before to explain also the precursor, and then we get a luminosity of the order of almost 10 to 51 erg per second. And this is, so this is consistent. Of course, this is isotropic. If you put a beaming angle, so it could be even higher by a factor of 10 if we use, for example, 10 degrees or so. So it is, in fact, consistent with the peak luminosity, with the luminosities of this precursor getting from a few 10 to 51 to a few 10 to 52 erg per second. So these numbers are quite interesting. Magnetic field and mass only at merger. Why? Because in general it depends on omega and the radius, but at merger this omega is given. You just take the Kepler law and put the merger at twice the radius of the stars, okay? And at then when you do that, it just cancels out the radius contribution and give this somehow universal formula just depending on B and M. But it's only at merger. So before it will depend, in fact, on the radius, of course. So you can even use this formula as a general, as a function of the radius, and estimate what will be the luminosity before the merger. And it will look to an increasing luminosity as they approach. And they approach this asymptotic value at the merger, or a peak value, if you wish, at merger. Okay, we can go and analyze the next step. That would be to analyze this UP phase. So this will be the second part of the luminosity, which is characterized by this spectrum, where we see this convolution of black bodies. This figure actually on the right is from the paper of 2016. It was already seen there that there was this possibility of looking at a spectrum as a presence of different black bodies of different temperatures, of course. And that was some interpretation that we gave there. Here, of course, we knew by this 2016 that the evolution of the dynamics of an electron positron pair plasma thermalized and expanding in a low baryon load medium, in a medium with a low baryonic matter, give a transparency temperatures in the order of photon energies in the order of MeV, and giving to thermal emission, to a black body emission of MeV energies. So it was, and it's from there that comes the idea that this prone emission is from electron-positron pairs evolving in such a way. But it comes out now the question of what is the origin of these electron-positron pairs, and why we have different temperature, different transparencies. And so we have an evolution, of course, of the system given to, we have a succession of transparencies somehow in the system, but very rapidly, of course. We are speaking about a phenomenon in very short time. Here we follow the origin, since we have this configuration which is very fast, this merged object. The electric field is very strong, apparently, from what we have there. We are going to analyze if the condition for pair creation from vacuum polarization is met already at the merge point. So the answer is yes. So how we can see that? So this is the, you can see there, this is the pair creation rate from the Swinger formula. And here we have to be careful, this formula there, this tilde E and tilde B are the electric and magnetic fields in the frame where they are parallel. This is important because this is come from the original paper of Swinger. Well, he compute this rate of density pairs in invariant way using the electromagnetic invariants that are here. These calligraphic F and calligraphic G. These are electromagnetic invariants, and it acquires that simple form there, the rate, only in the frame when they are parallel. You can express in this way. Why is this important? Well, it is important because we can define then the region where electron-positron pairs can be created using that exponential cutoff of the rate over there that you see, exponential of minus EC over E. So that EC is the critical field for vacuum polarization. This is roughly 1.3 times 10 to 16 volts per centimeter, or electron mass squared C to the cube over electron charge times H bar. Okay, is that EC there? But the electric field that appears there is the electric field in the frame where it is parallel to the magnetic field. So, so the condition that we will impose, so since that implies a very strong exponential cutoff of the rate when E is of the order of EC, when tilde E is of the order of EC, we define the limit of the region, what we call the other region, just because the extension from the concept of the iodosphere from Professor Ruffini work on the Reissner-Nostrom black hole in 1998 and then in the beginning of 2000, when they were defining this region of electron-positron pair around charged black holes. So this is not the iodosphere because it's not a sphere, because there is an angular dependence of this. So we define this region with this equation. Okay. Of course, there is not a sharp definition. You can see there it is not sharp, but this is the leading term giving the cutoff there. So This is an implicit equation for this R of theta, defining this region where you can create pairs. There is a simple way. This is this electric field in the frame where they are parallel. You can show that for this electromagnetic field structure can be approximated as the electric field that we saw before times the cosine theta. We have shown that this is occurs because the boost, the Lorentz boost, giving you to the frame where the electric and magnetic field are parallels is weakly relativistic, and then out of that you can show that this applies, and then you can, with that, you can show the, you can find an analytic equation for this, the other region. So the region where pairs can created can be found analytically. It's a solving a polynomial of a quartic polynomial. You can solve it analytically. And this is the analytic equation. This is not relevant where these terms are. What is important is to notice few things here. One is the angular dependence. Okay, there is an angular dependence. Second is that the largest extension is on the polar axis. Okay, and this is the largest extension you can see here. It acquires a very simple form. You see there, and you see again here we introduce this beta parameter. That is just the ratio of the magnetic field to the critical magnetic field. This critical magnetic field is the same in Gaussian units, is the same as the electric field. Of course, so it's electron mass squared C cube over electron charge times h bar. And in Gauss is 4.4 10 to 13 Gauss. So defining this beta parameter, this extension, largest extension of the region where we create pairs is given by this simple equation. And you can see the effect of the rotation and the size. And from this, so we can define what is the minimum magnetic field to, in such a way that this object create pairs outside, because this region have to be outside the radius r. So by putting this limit, you get this simple equation. So this is the minimum magnetic field to have pairs outside. So it remains to us to estimate what would be the rotation to have this minimum magnetic field, to create that. Then, of course, once you have that, you have your region of pairs, and you can estimate the electromagnetic energy available for pairs. Let me go here, and how we know what would be the rotation parameter of the star, of this merged object. I mentioned before at merger, just you have a square root, roughly square root of gm over merger radius cube from Kepler law. Well, what it is known, and from simulation, of course, at the beginning, you have a very deformed object. It's not just axisymmetric and very simple. It's not in rigid rotation even. But this, in some millisecond, a few milliseconds, it can go into the uniform rotation, the core of this merged core. I'm showing you here, this is an equilibrium plane of neutron stars, uniformly rotating. This is mass, this is central energy density of the star. The green curve is the Keplerian mass shedding sequence. This is the static, non-rotating sequence. And there is the axisymmetric instability sequence, this black line, where we expect, for example, black hole formation. So what happens to this merged object? This merged object, as it forms, it should enter into this region from left to right. From left to right, for example, at 2.4 solar masses, it goes there, enters over there. After it reaches that, and what is the frequency of rotation of a merged object at the green line? It's given here. It's given here. Uh-huh.
The black line corresponds to the maximum of the angular energy, or
These are sequences, these lines here that you see here, this dashed line, are sequences of constant angular momentum. So these are sequences of constant angular momentum, and that is given by all the, these are all the turning points. So they are maxima.
I thought it was shown that the instability for every star arises before the maximum, slightly before.
No, but it's not a general result. It depends on the equation of state. Yes, this criteria tells you, assures you that the configurations to the right are unstable. It doesn't tell you anything about the left. But from our computations, from the real solution, for the solution of the oscillation equations and the perturbations, the only in few cases it has been found some configuration in the left. Okay, very, very, very rare, but anyway, very close to the black. Okay, so so the configuration center this line, and this line, the frequency or the angular momentum of the configuration is given by this. This is the dimensionless parameter, angular momentum parameters of this along this grain line. Okay, for different equation of a state. This is something that we show in 2015, okay, that along the Keplerian sequence, okay, the angular momentum satisfies 0.7 m squared. It's 0.7 m squared from one solar mass over one solar mass. You see, almost independent of with very little scatter on the nuclear equation of state. So we know what is the angular momentum there. It's 0.7 m squared. And from that, we know what is the angular frequency there. It's 0.7 m over the moment of inertia. So we can get that, and then it should continue until it gets the black one. And that would be the point of black hole formation. And there must be the frequency at the black line have to be smaller than the frequency of that point. So if here is 0.7, the black hole should have an angular dimensionless spin less than 0.7 in this picture. And this is exactly what we find. Okay, we find from the GeV emission 0.22. From this reasoning, you can only say that has to be lower than 0.7. Not exactly what we did. What is the value? That is not wrong. It's just that we don't know what is it. We have only an upper limit. Yes. So you have an evolution of this merge core in this region, and in this region is where it should happen, the UPE. And we needed this omega, okay, to derive that. So what is the minimum? So the minimum magnetic field, we need the minimum angular frequency. And that minimum angular frequency we get is that when it forms the black hole, we have the GeV emission, but we don't have anymore the UPE phase. And so that is the minimum. This is the angular frequency that we are going to use to estimate the minimum magnetic field. But that we get only from the GeV analysis, okay? But I have to anticipate that analysis here. That's 0.22 that I just mentioned. And we got, when you put that, you get the minimum magnetic field, 2.10 to 14 Gauss, okay? This is the minimum magnetic field that gives you an induced electric field able to create pairs, okay? So this is the meaning of this minimum magnetic field. Right, this is what I was mentioning, 0.22 m squared over I.
For the UPE, you cannot have a UPE with magnetic field lower than this.
Exactly.
Okay. But it is,
so this is the minimum. And from this minimum, then, since you know that it enters into that region with 0.7, you can estimate what happened, for example, at 0.7. If you put 0.22, everything is 0. You don't have pairs, you don't have anything. So you have to make for larger values. But the larger values for the rigid rotation of the Newton star in that phase is 0.7. So we can estimate the energy of the pairs. The size of the other region on the pole is 5 kilometers. And typical energy, since the UPE energy is of the order of 4 times 10 to 52, but the energy available for pairs in this region is of the order of 10 to 45 roughly, you can derive that it's more or less like 10 to the unit is to happen like 10 to 7 times this process of formation. And of course, we see only in the analysis, because of the limiting, of course, you have the limiting fluxes, the threshold for the statistics of the UPE from the data analysis. We see only 8 black bodies there. Okay, we don't see 10 to the 7 black bodies. These are the parameters of the gamma. This is the Lorentz factor at transparency. These are the temperatures inferred from that plot of the analysis of the spectrum. So we have this T. This formula, therefore, the Lorentz factor at transparency, the baryon loading, and the radius of transparency comes from the works that works from Ruffini, Salmonson, Wilson, Swain, 1999 and 2000, and then in our analysis of long GRBs in 2021, 2022. And it depends, if you see the temperature, it depends on the size of the other region there. You see this delta D and this energy there of the pairs. And from that, we can derive these properties. So you see a range of different Lorentz factor at transparency, different range of these different baryon loading parameter and radius of transparencies of the order of 10 to 9, 10 to 10 centimeters. So those are the properties of these, transparency properties of this plasma that are observed in the UPE. And this conclude our analysis of the UPE. And then we have, after the UPE, we have these 3 spikes that I showed you already. These spikes are still before the GeV emission, so we assume that they are not related to the black hole, but they still could be related to the merged object. And this is a hypothesis that we have, that they could be related to quasi-periodic oscillations of the material. No, I go there. It's the next point. The next point. So this is related then with the difference between the spikes, the difference time. They can relate that this could be related to material, to precision frequency of the material around the merged object. So we derive some parameters for that. And they are consistent with the from QP observations of X-ray binaries. Then we go to the GeV emission that is related to the black hole. And then we start with this, the mass formula of the black hole, related the mass of the black hole, the reducible mass, and the angular momentum of the black hole. And we have to see how to constrain these values. How do we do that? Okay. So from our previous works in the analysis of long GRBs, actually not short, but we have shown that GeV emission can be explained by the presence of, by the Kerr black hole in a magnetic field. The rotation of the spin of the black hole coupled with the magnetic field induces also an electric field, and that electric field is able to accelerate particles that can radiate at GeV energies. And so, and in that model, it was the extractable energy of the Kerr black hole which should power the energetics of the system, of this emission. The extractable energy, or sometimes called rotational energy of the black hole, is the difference between the mass and the reducible mass of the black hole. And so this should power this energy of the GeV emission. If this is so, then the mass of the black hole is given by the reducible mass plus the energy. This is here, is divided here by c squared, by the energy of the GeV emission. And moreover, we can also calculate the spin. And the spin is given by this directly from the mass energy formula of the black hole, just by putting this over there, you get this. And so this, if we know the reducible mass at the GeV energy, then we derive the black hole mass. So the most important point is how to fit the reducible mass. And so the reducible mass here is fixed by the mass of the heaviest neutron star, observed. Because this is in these works of Romani et al. This is actually is the heaviest neutron star known is that of pulsar J0952 minus 0607. And from and the energy is clearly integrated. It's clearly integrated from the luminosity. Yeah, it's integrated, but if you integrate to the where you have data or infinity, the number is the same because it's a power law decreases. And from this work of Romani and collaborators, it was established the lower limit to the critical mass of non-rotating neutron star as 2.35 solar masses. And so that will be give a good proxy for the reducible mass of the black hole. If you do that and you compute the energy of the GeV emission by integrating the GeV luminosity, integrating the GeV luminosity over there to infinity, and and taking into account that in the modeling that we have of extractable energy, of the extractable energy taken out because of this radiation from accelerating particles occurs in a region of 60 degrees around the polar axis, then we get these energetics for the GeV, 2.5 10 to 52 erg, and the mass of the black hole and spins turn out to be this, 2.36, and the spin, the 0.22 that I already told you. No, the beaming angle comes from here. That's come from here. Yes, that's come from all the work. No, it comes from this. From that point, and this from this also, from this. This is the theoretical that agrees also with the observational part that this GeV emission appears to be emitted in a region of 50 degrees around the rotation axis of the black hole. Of course, if the beaming angle would be different, the mass of the black hole will be different and the spin. And so these are the reference where we do this work of the GeV. So this is the mass of the black hole and the spin of the black hole. And then from the X-ray afterglow, that will be somehow simpler in the sense that there is still the matter bound to the system and circularized around the newborn black hole, and then it would be of you should expect some accretion, and that can pay that luminosity. If you do that, you can compute the evolution of mass and angular momentum of the black hole, and the accretion, and estimate the amount of accreted mass during this time. And it comes to this small value of the order of 0.01 solar masses. Very small value. The same mass. That means that it's practically the same mass. And this is an important point. Okay, so then from all these numbers, we can make an inference on the gravitational wave emission during the merger, because from angular momentum conservation divided between the angular momentum of the black hole and the disk and the one radiated, you can, for all these, what we get is that amount of angular momentum radiated. If it is radiated only by gravitational waves, we can make an inference of the energy. during the merger of 3 times 10 to 52. And then we'll come to almost the conclusion. This is a summary of this, and you can see there, so the energies of the different phases. If you sum up all of that, then you see the energy of these objects of the order of almost 10 to 53. This is the mass, angular momentum, and parameter and reducible mass of the black hole. So the masses of the merging components are of the order of 1.2 solar masses. Magnetic field should be larger than 2 10 to 14 Gauss, and it could be up to 10 to 16. The gravitational wave is of the order of 3 times 10 to 52 in the merger, and that disk mass 0.01 solar masses. By the way, this is very much in agreement with simulations, okay, for mass symmetric mergers. Then these are some conclusions. The salient points is that there are strong magnetic and electric fields in these mergers up to from 10 to 14 to 10 to 16. And of course, this can have a role in the dynamics approaching the merger. And they suggest a revision of gravitational wave emission models of neutron star binary mergers to see what could be the role in the dynamics and in the gravitational wave emission itself. The induced electric field around the merged object is overcritical. So this is just to say that you don't need a black hole to create pairs. You can create the pairs before they form in the black hole. And it applies to different situations where you have an object with very strong magnetic field and spin. To get the pairs from vacuum polarization, you don't need a charged black hole. The conditions is met for the merged object before. So this is what we show, especially in this paper. Then the black hole mass and spin can be inferred from the GV emission and from the measurements from a massive neutron star, because it sets you the value of the irreducible mass of the black hole. And then, of course, the afterglow suggests a small disk around the black hole, so suggests mass symmetric binaries. This is in agreement with the distribution of masses of binary pulsars. Then the gravitational wave emission is much less than the electromagnetic emission, and this suggests a revision of the dynamics approaching to merger and the gravitational wave energy release near the merger point. Then is that this analysis seems not to be unique for 090510, and this is important because there are also other short GRBs observed, for example, with similar GeV emission, like we are showing here. And so the conclusions and the modeling that we are making here is very likely to apply also to those sources. And so it suggests also the possibility also to infer, for example, black hole masses there, spins, and all the other quantities that we are doing. And so we have some prospects from here, for example, in fact, inference of black hole mass, which constrain the neutron star critical mass, and vice versa, as we have shown here. And so, and then subsequently accretion of the band ejecta. So we are all these short GRBs telling us about this an important question to answer. Then we have not all short GRBs from black holes, of course. So then it depends on the merging masses, it depends on the different properties. And so we can, this is important to put constraints on the equation of a state of neutron stars. So this is something that is also interesting to do. And then to make simulations of the pair creation evolution in highly magnetized, fast rotating massive neutron stars, taking into account that the system is not spherically symmetric. And so under these conditions, there could be some difference relative to the spherically symmetric approximation that we have made here. Then, of course, we need the particle motion of charged particles around the newborn black hole. That could be nice work to do, taking into account different possible interaction between particles. The magnetic field feedback. The magnetic field feedback is also important, just to see if the pairs, for example, when you have the pairs, if they screen the magnetic field can be reduced. This is important
to see the transition of the magnetic field from the UPE to the GeV emission that is relevant. We have some first work on that from some 3 years ago. It would be nice to extend that work to this, and also to extend to different geometries. Not magnetic dipole, we can have the quadrupole, and they could have some difference. And then, of course, there is the black hole feedback, in the sense that we have considered that during the GeV emission, the reducible mass is constant, is kept constant, but actually it could increase some. And we have to evaluate how much the reducible mass increases during this process, but it depends on the process of energy extraction. We have shown that the increase of the reducible mass is very limited in electromagnetic processes. So this is important. So we have shown that, and this, in fact, is what that is why we assume the position of taking it constant during the process as a very good approximation. Okay, that's all.
Okay. Question? Before, yes.
So, you mentioned maybe at least qualitatively what is expected in the new numbers you obtain for the gravitational wave emission, when considering if it's respect to the traditional calculation where only per objects were accounted in the calculation?
No, that has to be done. We have some expectations from the.
Excuse me. Repeat again.
Yes, if you have yes, if you have some hint on the difference between your number obtained from the gravitational wave emission in this more general approach with magnetic fields respect to the traditional approach of bare objects, the numbers.
Okay, so the answer is no, because we have an estimate from all numbers for energy angular momentum conservation, or expectation from the energy radiated from gravitational waves. But we didn't have a simulation of everything making the gravitational wave emission and the electromagnetic together. Okay, that would be the next step to see what would be the effect. But for sure, what we are showing is that during the merger, the electromagnetic emission is huge. And so it could have an effect on the dynamics of the objects itself and to the gravitational wave emission. And even before merger, in the few milliseconds before, you have the interaction of the fields of the two stars that could also have differences in the gravitational wave emission. There are even some works studying that part.
Beautiful. But we have to stop, but at the same time, I would like to make sure. Okay, there is a question still.
Yes, how general might be this model related to, how it compares with gravitational wave produced by mergers of neutron stars, namely.
Okay.
Can you make
He gave the diagram. He gave the.
No, but I don't have a comparison between no electromagnetic fields.
No, excuse me. Just say what we have shown. Okay. Just not to create confusion and let Tilly come with a message. This was a long process studying binary neutron star and emitting gravitational wave, which was done by another part of my group, but mainly by Thibaut d'Amour in which you consider the two neutron stars just as bare massive particle rotating with spin. But even that approximation was not clear. The main that was done properly, namely if the particle were spinning, certainly it was a very nice work for particle just gravitating and in a binary, the Moore approximation. Then we did a paper 10 years ago in which we consider charged electromagnetic black hole and practically I decided to go back to that work and not to consider charged neutron star in binary, DLE, but to consider a neutron star with magnetic field. And with magnetic field of the order of 10 to the 14, 10 to the 16, whatever, the normal magnetic field of neutron star. In this paper, we finally did this computation, and the very interesting thing, which comes out for other application, is that was expected that the X-ray emission is very high in the MEV, and there is also in the JEV. From the MEV, you can find out that there is very strong emission of the order of 10 to the 52 in the UPA, which is observed in GRB. This is very important. It's observed and we found. And on the other side, we can study the way to determine, it's a technical point, the way of determining the mass of the black hole. And the new value, this is one of the first papers in which we have an estimate, not an estimate, a measure of the black hole mass in accretion system by neutron star. Okay, you have two neutron stars, you have accretion. What will be the mass of the black hole? And the mass of the black hole is of the order of 2.67. Is correct, the value 2.67? 2.56. No, the value of the neutron star critical mass is 2.35. 35. And this is 10 to the 37. 36. Therefore, it's a little more than the critical mass of the neutron star, but that order of magnitude. And this was made possible thanks to the value of the maximum neutron star mass derived by Romani. This has been very important because there is a value of the neutron star mass maximum observed in 2 times 10 to the 35, the Romani limit. And what we show is that the black hole created by two neutron stars is very, very close to that, few percent different. Now, this is the message we are giving, because this shows that out of a neutron star, we will repeat this also in GRB, that all the black hole coming from accretion into a neutron star are of the same order of magnitude, like this one, and we are going to publish soon. Therefore, the message is, if you take black holes formed by accretion on a neutron star in GRB, the mass is 2.37. This is the new message, which is definite. This shows that, of course, this does not tell anything. Maybe we will write, I hope we can write a note tomorrow after your talk or the day after. This has nothing to do with Cygnus X1, where we are speaking about mass much bigger coming out of the order at least of 10 solar masses. Therefore, that is a different channel, completely different, which you don't find in gamma ray burst. In gamma ray burst, you find this. This is a very new statement that Dili can bring home. In GRB, the maximum black hole that you can form is 2.37, whatever is this value, not more than that. And then there is another problem, which will be addressed tomorrow by Wang Yu, is what happens in a quasar. GRB tells this, okay? Cygnus X1 give another message, but we will see after the talk of Felix. But what happens in quasar? That will be the big discussion tomorrow. Why you need dark matter in order to form very big mass black hole. Are you there, Dili? How do you form very massive black hole? This will be the talk of Wang Yu. Yes?
Well, that you cannot get this 2.36. So there is a vacuum of black holes. There are no black holes with masses in between 2.4 or 5 and
10.
6, 7.
10.
That's so apparently black holes
Yes.
formed by this mechanism.
Yes.
That limit is consistent with the fact that black holes with masses of 3, 4 are not found.
Yes.
Observation.
Yes. Of course. It cannot contradict the data.
And the black holes that found usually have masses the order of from 7
Yes.
solar masses.
Beautiful. Beautiful. Okay. Right now, we have explained that no matter which GRB and so forth you consider, you cannot go to the other family. And this family is strictly due to the Romani limit, and is around 2.3, but less than 3 solar masses or so forth, well below. And what you are saying is something more, that if you do look at the data, over 2.3, you find the desert until you don't reach very much more massive object. This is very important. Now, the next talk, I don't know how we stand, is 1 o'clock. We have to break some time. I hope this message was clear, okay? I feel confident it's clear. It was long work. It's the confirmation of the result which we obtained 10 years ago. The only difference is we work on effective charge, and now we work on magnetic field. But you can go from one to the other with the effective charge concept which we introduced with OG, the effective charge concept. I feel quite happy about all this. But now what we are doing, starting to do, is a new topic. Are you there, Dili? The new topic is, from what we have learned on GRB, what can we go back and try to understand about supernova, about the relation of GRB with pulsars, with the remnant, and so forth and so on. In other words, the GRB are coming out as a paradigm to be used in order to prove and to study supernova and all the other fields. And already we know that GRB produce pulsar and so forth, but it's 1 o'clock. I think we have to stop because we have to go to lunch in the afternoon. Let's see. Maybe there is a room in the afternoon. There must be a room.
The first talk only takes like half an hour.
Who is the first talk? Okay. Therefore, we start at the regular time in the afternoon, and we will try to squeeze. Because we will come back to this just to present the new idea how to approach a supernova introduced by the GRB. What we have learned on GRB about supernova.
In the afternoon, we have a discussion in those about this.
Today?
Today, yes, in the afternoon. We can combine
Yes.
one talk and that discussion in one time. In
Yes.
the afternoon.
You're sure that is today?
Yes, it is today.
Ok, mi può portare il programma? Le mette 2 copie qua, aggiornato. Ok, good, we saved the day. You had a question?
Yeah, I have a question, but I think there is no
Oh,
time.
sorry.
Excuse me.
There was long ago, and for many times, the idea that gamma ray burst and the model of collapsars for gamma ray burst, namely that the formation of black holes could be related to gamma ray burst. What is your opinion? Because there people were saying that black holes with masses where gamma ray burst could be produced by the collapse of massive stars. Yes. Do you believe all gamma ray bursts are of this time?
Now we have enough data, and we need from this data, we need to have another kind of supernova, which is not the traditional one, and we will talk in the afternoon. But what we can say for certain is that the black hole is not formed at the beginning. It's only after 3 steps or 4 steps that the black hole is formed. After 3 steps. The black hole is not initial. The black hole comes after other steps, which we see.
For example, the black hole
No.
This is what my question.
Your question is no. GRB, now for certain, we know the black hole is 2 point whatever it is, okay? Therefore, Cygnus 1 is out for the GRB. But still on the GRB, you have, you can say, wait, what about the collapse? Well, still about the GRB, we will start in the afternoon, okay? You have that the black hole is not original, not the step number 1. The collapser assumed to be a black hole. Then you ask Zvi and so forth, what about how you form the black hole? No problem. We don't look at that. We assume. Okay, now we can prove that the black hole is not initial. It's not the starting point. The starting point we will discuss in the afternoon is a completely different topic. It's a new kind of supernova. And you will be shocked by this approach, because what we are saying is that a gamma ray burst has not only one supernova, but has two supernova. Two different kinds of supernova. Supernova per supernova and supernova leading to pulsar. This is in the afternoon. Okay?